When Carl Benz delivered the first car with a combustion engine, could he ever imagine what would happen 130 years later? In 2009 alone, about 61 million commercial vehicles have been produced, with the number of cars and light trucks on the road rising up to 810 million. The need for increasing road safety and green driving with an ever-increasing fleet of vehicles on the roads is more than ever apparent. Drivers are responsible for 97% of all accidents. Since the first intelligent transport systems were introduced, including basic applications such as parking guidance, car navigation, ADAS systems, a lot has changed. Wireless communications allowing V2V and V2I communication have become available, sensors at reduced cost as well. The following step was to increase substitution of the driver, both on middle and long term, corresponding to higher degree of automation. Highly automated vehicles can take over three main driving functions: steering, path planning, and navigation. The aim is to make driving easier for people and create highly automated systems which they can use intuitively. As part of the HAVEit project, 3 automation modes which can be selected and activated by drivers were developed and implemented. In the first mode, the driver steers the vehicle alone, assisted by already available standard driver assistance systems, such as lane keep assist or an emergency brake assist. In partly or semi-automated mode, the vehicle drives with longitudinal automation, so drivers no longer have to accelerate or brake. At the level of high automation, lateral automation comes into play, meaning the driver no longer has to steer. With high level of automation, additional challenges come up: how to optimally keep the driver in the loop, how to ensure optimal and safe termination of the automation, and how to optimally distribute tasks among the driver and the co-system. The need for assistance strongly depends on the varying performance level of the driver. Higher degree of automation in this context means to support the driver in monotonous driving tasks, as well as in highly demanding tasks. HAVEit, from concept to reality. HAVEit aims at reducing the driver's workload, preventing accidents, reducing environmental impact, and making traffic safer by supporting the driver in his or her tasks. Driver monitoring is used to estimate the driver's performance and state, including driver distraction and driver drowsiness. Automated driving requires an adequate safety architecture, from fail-safe to fail-tolerant. Therefore, a scalable vehicle architecture has been chosen for the migration from single advanced driver assistance systems, ADAS, to a powerful automated driving concept. Comfort, safety, and the efficient usage of energy are addressed by the HAVEit highly automated vehicle applications in passenger cars as well as in heavy-duty trucks. In order to improve traffic safety and efficiency, HAVEit set a number of goals from the very beginning. First, to develop and validate the next generation of ADAS with an optimized task repetition between the driver and the highly automated vehicle. Second, to optimize system joining and interaction between the driver and the co-system by defining different degrees of automated driving. Third, to develop and validate a scalable and safe vehicle architecture that includes advanced redundancy management in order to suit the needs of highly automated vehicle applications. HAVEit architecture. Sensors. Various external sensors are used to achieve a wide enough perception area for all applications. Especially for safety-related ones, effort is given to achieve coverage of the area of interest from multiple sensors. Sensor fusion uses a redundant and overlapping sensor setup to achieve robust and accurate road environment perception. Such perception is necessary for highly automated driving. Driver monitoring. The driver is monitored directly and indirectly all the time to obtain a confidence value on his capacity and attention status in order to optimize the task's repetition and the feedback strategy. Platform. A scalable vehicle architecture by means of smart sensors, standard fail-silent ECU, and smart actuators is defined to cope with the needs for highly automated driving to allow autonomous driving. HAVEit, co-pilot and mode selection unit. Starting point for the generic joint system is an intelligent co-system Let's start with sensor data about the environment, sensor fusion, and the generation of trajectories. Data is used to control the vehicle in relation to the automation mode that gets determined between the driver and the automation via a driver interface and a mode selection unit. A driver observation system estimates the driver state, especially driver distraction and driver fatigue. To minimize underload and overload of the driver, a layered approach of dynamic task repetition between driver and co-system is used, starting with a state-of-the-art layer and expanding to more future-oriented layers that give the co-system more authority and allow for a more fluid transition of control. On the first layer, the co-system proposes available automation levels. The driver can activate these automation levels with buttons or a stalk. As a second layer, the co-system actively urges the driver to change automation levels. Automation levels can be changed more fluidly by the driver or by the co-system in the third level in case of danger, for example. 2 rapid prototyping platforms are available in HAVEit. A new steer-by-wire system was developed and integrated in the DLR research vehicle FastCar 2, the vehicle where all HAVEit concepts were migrated. In place of a mechanized steering rod which links the steering wheel to the steering shaft, the steering input is transferred electronically by wire. Whereas the steering wheel in today's vehicles moves according to steering motions, the steering wheel in the FastCar 2 can remain motionless during automated driving, or support the driver with suggestions during normal driving. The more trucks and buses there are on the open road, the more important and critical are their braking performance to avoid crashes and blocked motorways. Over the years, new brake system technologies on commercial vehicles have been developed and introduced. Brake-by-wire is a new method of transferring the power of a vehicle's brake pedal to the brakes. By-wire, in this case, means the new system transfers the brake force electronically instead of pneumatically. The now fully electromechanical brake system results in an improved stability control and reduced stopping distance by about 15% compared to a state-of-the-art brake systems. Automated queue assistance. The Aqua system relieves the driver of the monotonous task of driving in traffic queues. When the system is activated, the driver can lean back, relax, and monitor the system's performance while the assistant controls the vehicle. Based on the environmental information, the system can decide on appropriate acceleration, deceleration, and steering, and thus calculate driving speed and steering activity accordingly. Automated assistance in roadworks and congestion. Complex situations often occur when driving through roadworks. Narrow lanes and curves, ambiguous lane markers, changing speed limits, and other vehicles driving closely beside. Challenges for both the driver and the system. The assistance system assumes partial control of the vehicle in a longitudinal direction and when moving to either side. The system recognizes demanding traffic lane instructions and, to an extent, even contradictory lane marking arrangements such as cones, concrete walls, central dividers, or yellow road markings, in addition to detecting other road users who may be pulling out, cutting in, or driving alongside. Temporary autopilot. The temporary autopilot drives us to vehicles of the future, integrating 3 different levels of functionalities. The pilot functionality, which practically introduces hands-off driving, for example when driving in a traffic jam. Assisted driving, where the driver is in the loop. This can be applied by driving in normal traffic mode, for example driving when traffic jam terminates. The third level is represented by intervening safety functions, for example driver-initiated emergency braking. Active green driving. The reduction of CO2 emissions is heavily pursued the last years. Active green driving aims at improving fuel consumption and efficiency by using environmental information such as e-horizon, forward-looking sensors, and dynamic traffic information. With the information obtained, the power split between the combustion engine, ICE, and the electric motor are adapted to use the energy storage in the most efficient way. HAVEit is paving the way for highly automated vehicles of the future, introducing novel approaches. Instead of just switching off an ADAS system in case of an impending potentially critical situation, HAVEit introduces a progressive, step-by-step approach to keep the driver in the loop, gaining and transferring the driving task to and from the automated system to the driver. 7 cutting-edge vehicle applications for both passenger cars and trucks, aiming at improved safety and comfort, as well as improved energy efficiency, were introduced, contributing to the reduced fuel consumption and reduced pollution to cope with the increasing road traffic problems. What the future will bring to the next generation of highly automated driving? HAVEit has set the way forward by introducing the research concepts of tomorrow.